Hello, and welcome to CS103 Part 2. So you'll notice that I'm not John. My name is Jules Hedges, and I'll be your captain for CS103 Part 2. We hope that you will have had your first synchronous lecture before you're watching this video, but we don't know for sure, so I'm going to repeat what we will tell you in the first synchronous lecture, which is that this term CS103 is being lectured by me together with Connor. So in the synchronous lectures, you'll see us together as a double act. The exploration videos like this one are going to be recorded mostly or entirely by me. Connor is also doing a lot of work in the back. He's producing all of the software that you'll be interacting with in this course. Okay, with that administrative things out of the way, the first topic of CS103 Part 2 is proof. This is going to build partly on what you've already learned about digital logic in CS106. So let me start by reminding you about logical formulas. We have a few ways of constructing formulas. So if P is a formula and Q is a formula, then P and Q is a formula, and also P or Q is a formula, and also not P is a formula. We also have some things which I will call atomic formulas. So these look like A, B, and so on. So in digital logic, the meaning of an atomic formula is something like the value flowing in this wire is a 1. In this course, the meaning of an atomic formula can also stand for other things. For example, it could be the value of x at this point in the program is 3, or it could be this program terminates. In theory, it could also be something totally different, like it could be the moon is made of green cheese. But we are computer scientists and not philosophers, so you'll be happy to hear that I won't be doing silly things like that, and the meanings of atomic propositions are only going to be things that are relevant to computer science. I'm going to introduce one more way of constructing formulas that you might not have seen before, which is P implies Q, drawn as a little arrow. Let me draw that a little bit more clearly. P implies Q. You can also read it as if P, then Q, or if P is true, then Q is true. Now, on to proofs. The idea of a proof is that it's a logical argument that a logical formula is true. So if you're a mathematician, you learn to write proofs in English or some other human language. But in this course, we're talking about something a little bit different. We're talking about formal proofs. So these are proofs in a formal proof system, just like other formal systems that you've already learnt about. So a proof is an argument that if some hypotheses or assumptions are true, then some conclusion is true. So it's an if-then argument. We're going to collect all of that information together into a piece of syntax called a sequent. So a sequent is a piece of syntax that looks like a list of formulas, which are the hypotheses, like this. So these are the hypotheses, also called the assumptions. And then a symbol called the turnstile. And then at the end, another formula called the conclusion. So you can read this as a thing that says, if the hypotheses are true, then the conclusion is true. So you shouldn't confuse the turnstile with the symbols that are allowed to appear in formulas. This is a different symbol, and it doesn't really mean anything. It's a symbol that's used to separate the hypotheses on the left-hand side from the conclusion on the right-hand side. Okay, so just like we build formulas using logical connectives, we are going to build proofs using things called proof rules. So here's an example of what a proof rule looks like. So suppose we want to prove a conclusion like P implies Q. So how do we prove that? How do we prove that if P is true, then Q is true? Well, one way we can do it is to assume P as a hypothesis and then prove Q. So the proof rule that says this will be written like this. So we have the thing that we want on the bottom, and then we have a line, and then on the top we have the thing that we need. So what this says is that if we have a proof of Q from the hypothesis P, then we can build a bigger proof of P implies Q from no hypotheses. This proof rule has a name. It's called implies I, for implies introduction. And actually, this isn't quite the complete proof rule. We might want to prove that P implies Q from some other hypotheses. So we might have some R1. We might just have some extra hypotheses here. And to prove that P implies Q from those hypotheses, how do we do it? Well, we prove Q from the same hypotheses together with the extra hypothesis P. Okay, so I'm going to show you a very simple example of a complete proof. I should have kept this on the screen. Wait just a second. R1, Rn, R1, Rn. Okay. So I'm going to prove that if P is true, then P is true. So we're going to start with a sequence with no hypotheses, because we don't need any extra hypotheses. And then we're going to have P implies P on the right. So this looks like an instance of the implies introduction rule. So we can draw a line above it, and then we can write this sequence, P turnstile P. And then we're going to label this with the name of the proof rule that we just used, which is implies I. So in order to prove P implies P from no hypotheses, what we now have to do is prove P from the hypothesis P. So what do we do next? Well, there's another proof rule which says that if my conclusion is already one of my hypotheses, then I'm done. So this is a sort of atomic proof, kind of like we have atomic formulas. So I'm going to draw a line above this to say that I'm done. And that is a complete proof of P implies P. Okay, so that was a very simple example. Here's a slightly more complicated one. So you can probably guess that if P, then P is true. Here's a less obvious one. P implies Q implies P. So maybe it's not intuitively obvious that this is true, but it is true. Okay, so we start with what we want, which is P implies Q implies P. This, again, looks like an example of the implies introduction rule, so let's use it. So to prove that P implies Q implies P, we have to prove that Q implies P from the hypothesis P. Okay, so what now? Well, the thing that we have now also looks like an instance of implies introduction, so we can use it again. So here it's not so obvious because we're relabeling. So the thing which was called P here, that's not working. There we go, is now a Q. But I can apply the same rule again. So to prove Q implies P from the hypothesis P, we have to prove P from the hypothesis P together with Q. And now we're done because the conclusion that we want, P, is one of our hypotheses. So I can draw a line and that says we're done. Okay, this was an introduction by example to formal proofs. So in the next video, I'm going to be much more precise and I'm going to tell you more systematically what are the rules of the game. So what are the rules of this formal system?